All right, like I just said, we're going to go over some circuit problems. So let's start off with this series circuit we have up here. And one thing that I like to do with these problems is always use a VIR table. That way you can keep yourself organized. Otherwise, I find your work tends to go crazy all over the board. So on this first one, we need to find, in this circuit, the total resistance. Then we find the total current. Then we find the current in each of the resistors, and then use that to solve for the voltage across each of the resistors. Now, one thing, and we're going to go through number 23 and 24 together just so that we feel good on it. And then once we're doing okay, hopefully we got the concepts. You guys are going to try out 25 on your own. So in this first one, let's just write down what we know already. We know that our total voltage is 120 volts, so I'll put that down here. We know the resistance of 1 is 25 ohms, 2 is 16 ohms, and 3 is 47 ohms. Let's see, is there anything else that we know automatically? Nope. So first thing I want to do is find out our total. Since these guys are in series, it's pretty simple. We just add them up. 25 plus 16 plus 47 gives me a total resistance value of, let's see here, 88 ohms. Let me double check my math on that. 25, 16, 47, 11, 8, carry the 1, 8. Beautiful. All right, now that I know that, I can solve for my total current. Current is equal to voltage over resistance, so I equals V over R. It's 120 over 88. When I plug that in, I get a current of approximately 1.36 amps. Cool. Now, because this is a series circuit and there's only one pathway for the current to flow, that means the current's got to be the exact same everywhere. So all of these are going to be 1.36 amps. Hey, that's pretty neat. Now, if you feel like you can do the rest of this on your own, go ahead and try it. In 1 second, I'm going to tell you what I'm doing. Neat. So here we go. Voltage equals current times resistance. So all I'm going to do is multiply this across, multiply this across, multiply this across. And because it's in series, I know that all of the voltages should add up to the total voltage. So let's do that. 1.36 times 25 is going to give me around 34 volts. On these problems on quizzes, as long as you're relatively close, I'm not going to take points off. Then we have 1.36 times 16. I'm going to get about 22 volts. And then finally for the 47 ohm resistor, I'm going to get approximately 64 volts. Now let's try this out. 34, there is the bell. When I add these up, that gives me a 0. Nice, carry the 1. So that's about 6. Oh, look at that, 120. That works out great. Now let's come over here and try it out on our parallel resistors, or our parallel circuit. So first thing, is there anything I know automatically? I know my voltage is 120 for the total circuit. I know my resistors are 25 ohms, 16 ohms, and 47 ohms. Is there anything else I know automatically? Well, I know it's a parallel circuit. Parallel circuit, as long as there's no series sections, all of my resistors are going to have the exact same voltage as my battery. So 120 volts, 120 volts, 120 volts. Hey, this is pretty nice. Now all I need to do is solve for the current. So I can either solve for my total resistance, or I can just go through and solve for all these currents. But I still need to know my total current that comes out of the battery. So let's solve for resistance first. The way I do that is I'm just going to take my resistors. So R total is going to be 1 over each of my resistors. And then I'm going to take 1 over that answer. And when I plug that in, I get a total resistance of approximately 8.1 ohms. Now notice, you should always end up with a lower value unless you have like really small resistances. You're going to always end up with a lower value for your total resistance when you're in parallel. So I get 8.1 ohms. And that should work because a lower total resistance will give us a higher current, which means that current is going to spread smaller values out through here. So now let's just solve for it. Every single one of these, V divided by R gives me I, because rearrange V equals IR, V over R equals I. Boop. So now I'm just going to go down the list, plug into my calculator, solve for these. I get about 14.9 amps here. And then for each of these, 4.8 amps. 120 divided by 16 is going to give me 7.5 amps. And then finally, on my bottom one, I get 2.6 amps. Notice the higher the resistance, the lower the current. And it looks like it's working pretty well. Highest, second highest, third highest. Now, if I add all three of these up, I should end up with approximately that number because the current that flows into here and into those ones it's splitting up and going through all those branches. So let's add them up and see if it works. I don't need units when I'm adding. All right, let's see. That'll give me 13 plus 6 is a 9. Carry the 1. So that's going to be 7 plus 7. That's 14. Hey, look at that. That works out. So if you're feeling pretty good on this, I'm going to put problem 25 up, and we'll see if you can solve it on your own before we work through them together. Okay, here's problem 25. I want you to go ahead and give it your best shot. I will tell you that the best way to do this is to try and simplify the circuit before you get started. Right now, it looks pretty ugly, but you can get it down to an equivalent or total resistance. Go ahead and give that your best shot. Write in the information you know to start, and we'll be back in just a few seconds to go over how to do it. All right, we can check how you did so far. So first thing I looked at was, I'm like, ooh, this is gross. I don't like this. What I'm going to do is I'm going to try and simplify it as much as possible. And the first thing I can do is simplify any series section that is in a parallel branch because I can only add up single resistors that are in parallel. So what I'm going to do is combine these two to find the equivalent resistance of this branch, which since they're in series, just add them up. So now I have this circuit. And notice this looks a lot easier to solve than this. All I did was I moved this into a smaller section so it's easier to see that it's parallel. A lot of times you're going to get on a problem and be like, I have no idea what I'm doing. Redraw it to make it simpler for your brain. Trust me, it's going to help you out a lot. So now that we have this here, I'm going to combine these parallel sections. Remember, parallel, we add the inverses and then take the inverse of the sum. So now I just have 3 resistors in parallel. I solve for my R tote, and when I do that, plug 5 in for every single value, and I get a total resistance of 13.3. Now, current equals voltage over resistance, so I take voltage total divided by my total resistance, and I get a current of 1.35. From here, I see that this resistor and this resistor are in series with my battery, meaning that they should have the exact same resistance value. So 1.35, the same current value. There we go. That's pretty much straightforward right there. Now I can solve for their voltages. Let's take a look. Beep, 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 beep. I'm going to take V equals IR. When I plug those values in, I'm going to get a voltage of 6.75 volts. Now, what I've figured out from this, if we come over here and look at this circuit, that means 6.75 gets used up here, 6.75 gets used up here. When I go in series, I'm adding them, meaning every time I go past one, I subtract from my total. So I would do 18 minus 6.75 minus 6.75. Whatever's left over is going to be the amount of voltage that's through this branch and through these branches. Based on that, I know that, let's see here, the remaining amount should be 4.5 volts. Since R3 crosses the whole thing, I know R3 is going to have that amount. It's going to have 4.5 volts. Now, across R2 and R4, those are going to add up to 4.5 volts. However, I don't know how much it's going to be in each one. Now, on this problem, I do because they have the exact same resistance, meaning that they should have the same amount of voltage across each of them. But let's just pretend like they don't and see how we would solve if we did. So now what I need to do is solve for the current on this side. Voltage divided by resistance gives me current. So 4.5 divided by 5 gives me 0.9 amps. What that tells me is coming up to this branch right here, I have 1.35 amps going in. Over on this side, I have 0.9 amps, meaning the remaining amount should be going on this side, which is going to be 0.45 amps. So I can come over here, and I know R2 and R4 are going to have 0.45 amps. Hey, that just kind of makes sense that 2/3 of the current is going to go on the side that has 1/3 of the resistance. 1/3 of the resistance, 1/3 of the current will go on the side with 2/3 of the resistance. Nice. Well, now that we know that, we can just go ahead and solve for voltage. Since they're in series, they're going to have the same current. So let's solve for our voltage now. 5 times 0.45 is going to give us a value of 2.25 amps. Sorry, volts. And 2.25 volts. Hey, look, that adds up to the 4.5 that goes across that branch. So if you feel pretty good on this, great job, you got it. Next set of notes, we're going to be going over Kirchhoff's rules, which will help us when we get into more and more difficult circuits. But for now, you should feel pretty confident on these simple circuits.